So in the receiver order characteristics, we compute two series, a false positive rate series that is on different thresholds, which we saw, of course, is the proportion of rocks that are identified as mines, things that are falsely recognized as mines when they're not, and that's false positives divided by true negatives plus false positives. And a true positive rate, which tells us what proportion of actual mines, is the same as recall, are identified as mines. So we compute these two, and then we plot them as we saw in our classification analysis digression, so to speak. We plot them in a curve, and we want to find out how good our model is by looking at these kind of things here. So let's take a look at that. So first thing, before we go to ROC curve, let's see if our model is discriminated at all or not. So what we can do is we can take our data and look for wherever the thing was actually wherever our case was actually a mine, we identify those ones and say these are the ones that were identified as mines. If the prediction was also a mine, so we have a mine that's actually a mine and the prediction is a mine, then we store that in an array called positives. And if the prediction was not a mine, then we store that in whatever prediction we get in the negatives, right? So what we want to find out is whether things that are actually mines were recognized as mines and things that are actually rocks were identified as rocks or not. So we do that, and we can draw a little curve over here, and that's what this is doing, which sort of histogram, which tells us that these here were mines that were actually recognized as mines, and then as we go further south, they were recognized. So the 0.06 values, these are our actual values, not our zeros and ones, but the actual predictions, the continuous predictions between 0 and 1. And so this tells us that yes, we have some kind of discrimination, but not perfect, right? So in this, the greens are rocks and the blues are mines, but our recognition, if you have a threshold, say if you put a threshold at 0.8, for example, then we pretty much have everything correctly recognized as a mine. If you put our threshold anywhere below that, things get a little bit messy, right? So this is what this is showing us. So if the greens and the blues are perfectly separated, then our model has done a great job of separating. But here we have some rough idea of that. But more interesting than that is what happens in a holdout sample. So we do the same thing with the testing sample, and we find that it's a lot more messy, right? In the holdout sample, we have a lot of greens that are intruding onto the blues, so that's not so great, right? Still, we can see that if you fix a threshold between let's say 0.625 and 0.75, somewhere there, we will get some kind of a separation. We're going to get a lot of false positives and false negatives, but there will be some kind of separation. So that's one way of looking at it, but we look at it with an ROC curve, and sklearn has its own ROC curve package, so we'll use that. And what the ROC curve does is, given a y, actual y, that's the zeros and ones that were actually in the training sample here, and given our predictions, and these, remember, are continuous values, the ROC curve is going to run through the predictions at different thresholds and decide whether they're zeros or ones, and compute the false positive rate and the true positive rate. And then we can plot that in a curve. So just to show you what that is, I'm going to take this. Maybe I've done it here. No. I'm going to take this, insert a cell above, and well, let's look at that and look at the area. So this tells us the area under the curve is 0.98, which is like humongous. So our prediction, this has actually a very stable kind of model, if nothing else, right? And we can see the actual values also. So we have FPR, TPR thresholds, and look at them. So this tells us these are the FPR rates. We see they vary 0, 0, 0.1014 all the way to 1, and the true positive rate is 0.01. Well, that's not so good, but 0.74, 0.74, 0.85, 0.85, blah blah, and the array that the thresholds that we get, because our data actually thresholds it's continuous, so it's rather than being from between 0 and 1, they're varying from -0.47 to 1.44, but that's okay. So that's that's what the ROC curve is doing. It's just looking different thresholds and plotting TPRs and FPRs for that. So we can plot these in a nice little graph and take a look at the curve. So we get a curve here that looks like this. So this our in-sample ROC curve has an area under the curve of 0.98, and we find that it's reasonably stable, right? So if we work anywhere in this middle area that is not at the edges of the orangish curve, assuming that's orange, but you know what I mean, then we should be in a fairly stable area where moving the threshold this way or that way is not going to affect our results too much, okay, assuming that we don't know what the trade-off between TPR and FPR is, right? I mean, that's the goal here. If we know the trade-off between TPR and FPR is, we can pick a threshold, but we want to be picking a threshold in the middle anyway, because that's likely to be more stable when we get new results or new cases coming into our model. But of course, that's our training sample, right? So what we really want to do is look at the outsample ROC curve. So let's draw that. And we find the outsample ROC curve doesn't look as great, but it's still not bad. 0.84 is still pretty good. And we still find that the area in the middle, somewhere from a threshold of, let's say, 0.25 to 0.8 or so, is a reasonably stable threshold area. Again, at the extremes, it's not great. At the extremes, we find that a small change in threshold can cause a huge change in the curve, and that's not what we want. We want to be working inside the stable area. So that's the way to look at this stuff. And so what the ROC and AOC curves give you is, and the AOC number, the area under the curve, gives you is a good idea of how good your classifier is and how sensitive it is to changes in the threshold. Too sensitive is not good. And so you don't want to be too sensitive. And so roughly what we want to do then is we want to figure out what should our model do. I mean, we've gone through all this analysis, we have precision, we have recall, we have all kinds of stuff, but we don't know what is it that we want to finally do, right? What threshold should we pick? So generally what you want to do then is you want to look back into the domain and try to figure out what the cost of picking a particular threshold is going to be. In other words, what is the cost of the true positive rate versus the false positive rate, precision versus recall, depending on your model. That's what is the most important thing here. So let's take an example. Let's say that everything that's classified as a rock needs to be checked with a hand scanner at $200 a scan, and everything that's classified as a mine needs to be diffused at $1,000 if it's a real mine, or $300 if it turns out to be a rock. So we have cost numbers here, and you can pick anything, like the cost, for example, if human lives are involved, if the mines are small mines that will injure people, if they're big mines that will blow up people, you can decide, you can try to put a cost number to it, and I don't necessarily mean dollars, but maybe a utility number, right? So anything that measures whether something is good or bad, essentially. What you're picking, the result, the positive and the negative outcome is good or bad number. So here, let's say we want to be with these numbers. What we want to do is we want to first get a confusion matrix. We get a confusion matrix on our test sample, not on the training sample. And let's say at this point, and you want to probably do this for more continuous numbers, but we'll say we'll take two extremes, 0.1 and 0.9, and say, all right, what's the cost associated with the threshold of 0.1? So we get back our true positive rate, false positive rate, etc., and compute a cost over here. So the true positive rate is CM0. Confusion matrix will return the true positive rate at CM0, and we know that that's telling us that something is a mine when it is actually a mine. So that's $1,000. We're going to go and test it, right? So it's going to be $1,000. Then the next is the false positive rate, which tells us that something's a mine, but it's not a mine. So that's going to cost us $300 because we send someone to do it, to test it, and it turns out to be a rock, and we spend $300 trying to figure that out. The next is our false negative rate, which is, it doesn't matter in this case, but this is what tells us it's a rock. If it's a rock, it costs us $200 to check it and make sure that it is actually a rock. And if a mine is classified as a rock and we can check it, and assuming nobody gets blown up, then that costs us another $200, right? Am I right about this? Let me see. Yeah. Yeah, these are classified. So it could be a different number here, because if it's a rock, you classify as a rock and it turns out to be a mine, you might get blown up. But in this example, let's just say we are safe. We go and test it. It costs us $200, but it doesn't kill us, right? So that gives us a cost for 0.1, and then we can run the same thing for a threshold of 0.9 and see what we get. So we get a cost here that says at 0.1 it costs us $41,100 on our training sample, and at 0.9 it costs us $24,800. So let's take another example, and we said everything that's classified as a rock would be assumed a rock, and if it's wrong, it'll cost us $5,000 in injuries, treatment of injuries or whatever. So whenever something is classified as a rock and it turns out to be incorrectly classified, that means it doesn't be a mine, it costs us $5,000, but otherwise it doesn't cost us anything. So we are walking through the field, we're not testing anything at all. So here in this case, the only thing that we care about is this one over here, that is a false negative, where it says it's a rock, but it turns out to be a mine. So we again take 0.1 and we compute the cost. So this is 5,000 times this, and everything else is 0. And we do the same thing for 0.9. It's 5,000 for this, and everything else is 0. And we run the cost, and we now get that 0.1 threshold is going to cost us $10,000, but a 0.9 threshold is going to cost $105,000. So we can see that in these two cases, our results are different depending upon our cost structure. If our cost structure corresponds to this case, then we will pick a 0.1 threshold, a 0.9 threshold, because that's better, right? 24,800 is lower than 41,100. Whereas in this case, we would probably pick the 0.1 threshold because that's better, right? So it's a question of how we want to use the results, what the cost structure in our real world domain is, and that is what controls the choice of threshold more than anything else in a classification problem. So that's it for using regression for classification. I urge you to try logistic regression on your own and seeing what kind of results you get, and then compare that with the results we got for this. And next week we're going to look at a couple of other machine learning models and some other examples. So until next week, thank you.